HabEX, the future telescope for exoplanets. This isn't a sunflower. These are the unfolding steps of the Starshade of a space telescope. Its name is HabEX, which stands for Habitable Exoplanet Observatory. But what is the Starshade? Well, among all the methods astronomers use to observe, find, and track exoplanets, there is the so-called direct image method. It consists of literally taking a snapshot of an exoplanet, possibly an Earth-like one. Needless to say, this is a difficult task, perhaps one of the hardest goals that astronomers are trying to reach nowadays. In fact, exoplanets don't like being under the cameras, and also the star is way brighter than its exoplanet. This makes it hard to find it, but we can get rid of the starlight by placing an obstruction, and the Starshade acts exactly as an obstruction to block the undesired light from the star. This telescope will bring us to brand new knowledge about our universe and the existence of life as we know it on other planets in the galaxy. Keep watching the video if you want to know more about it. I'm sure you won't regret it. The Habitable Exoplanet Observatory, HabEX, is a concept for a mission to directly image planetary systems around sun-like stars. As we were saying, nowadays we have a lot of methods to find an exoplanet, but all of them are biased. Among the so-called indirect methods, we have the radial velocity measurements from a star. By looking at the changing of wavelength in the spectrum of the star due to the Doppler effect on the line of sight, we can tell what's the effect that an eventual planet induces on its host star, and therefore we can try to classify the exoplanet. Another method, for example, is the transit method. When a planet passes in front of a star, we may see the star becoming dimmer for a while with a decrease in luminosity proportional to the mass of the planet. When it happens, we are able to tell something about the revolution period of the planet and its mass. These are well-known techniques that allow scientists to find a lot of exoplanets, but most of them offer us a small range of masses and radii, which means we are biased. For example, we are able to find a lot of hot Jupiters, Jupiter-like planets that orbit very close to their host star and therefore are said to be hot. Finding Earth-like planets is quite challenging, yet it is very important if we want to acquire information about life as we know it and how it forms in the universe. That's how the hunting for exoplanets translate into hunting for life, and we can say we live in an era where we are starting to look for them, and we will probably find something important in the next 2 or 3 decades. What a time to be alive, huh? HabEX will be, of course, sensitive to all types of planets. However, its main goal is, for the first time, to directly image Earth-like exoplanets and characterize their atmospheric content. In order to understand this point, let's see how the direct imaging method works. Planets are extremely faint light sources compared to stars, and what little light comes from them tends to be lost in the glare from their parent star. So in general, it is very difficult to detect and resolve them directly from their host star. Planets orbiting far enough from stars to be resolved reflect very little starlight, so planets are detected through their thermal emission instead. It is easier to obtain images when the star system is relatively near to the Sun, and when the planet is especially large, considerably larger than Jupiter, widely separated from its parent star, and hot so that it emits intense infrared radiation. Images have then been made in the infrared, where the planet is brighter than it is at visible wavelengths. In order to block light from the star, we use coronagraphs. During a total solar eclipse, the moon acts as an occluding disk, and any camera in the eclipse path may be operated as a coronagraph until the eclipse is over. More common is an arrangement where the sky is imaged onto an intermediate focal plane containing an opaque spot. This focal plane is re-imaged onto a detector. Another arrangement is to image the sky onto a mirror with a small hole. The desired light is reflected and eventually re-imaged, but the unwanted light from the star goes through the hole and does not reach the detector. Most coronagraphs are intended to view the corona of the Sun, but a new class of conceptually similar instruments, called stellar coronagraphs to distinguish them from solar coronagraphs, are being used to find extrasolar planets and circumstellar disks around nearby stars, as well as host galaxies and quasars and other similar objects with active galactic nuclei, AGN. Building and using a coronagraph is not as simple as it seems. The instrument design must take into account scattering and diffraction to make sure that as little unwanted light as possible reaches the final detector. HabEX will use a special coronagraph which is called a starshade. This short video illustrates how a starshade is deployed and how it blocks the light. A starshade of radius r located at a distance z from a telescope creates a dark shadow, which suppresses the starlight while allowing the faint exoplanet light to enter the telescope unimpeded. We can think of the starshade as consisting of two components, a central circular disk and radically tapered petals attached to the disk. The central disk serves as the occulting spot that blocks the on-axis source and creates a geometric shadow that covers the telescope. However, as we just discussed, the light will diffract around the sharp transition of the disk's edge, spoiling the darkness of the shadow. This is where the petals come in, to create a smooth reduction in the transmission of the disk to reduce the diffractive ringing caused by the sharp truncation of the electromagnetic field. This process is called apodization, and it is a common problem in optical design and engineering. The planets detected through direct imaging currently fall into two categories. First, planets are found around stars more massive than the Sun, which are young enough to have protoplanetary disks. The second category consists of possible sub-brown dwarfs found around very dim stars, or brown dwarfs which are at least 100 AU away from their parent stars. Planetary mass objects not gravitationally bound to a star, such as rogue planets, are found through direct imaging as well. Talking about rogue planets, if you want, you can take a look at our previous video. Here's the link. By measuring the spectra of these planets, HabEX will search for signatures of habitability, such as water, and be sensitive to gases in the atmosphere, possibly indicative of biological activity, such as oxygen or ozone. How is it possible? Well, the spectrum looks like this. And the lines you see are created by the presence of the corresponding elements. If a planet contains oxygen in a precise state, you will find oxygen lines in its spectrum. The same happens if the planet contains water molecules. Knowing those lines positioned by laboratory experiments, astronomers are able to tell us whether the planet is a good or a bad candidate. HabEX would search for potential biosignature gases in exoplanets' atmospheres, such as O2 at 0.69 and 0.76 microns wavelength, and its photolytic product ozone, O3. A further infrared capability of 2.5 microns would allow searching for secondary features such as methane, CH4, that may be consistent with biological processes. Molecular oxygen, O2, can be produced by geophysical processes, as well as a byproduct of photosynthesis by life forms. So although encouraging, O2 is not a reliable biosignature, and it should be considered in its environmental context. In addition to the search for life on Earth-like exoplanets, HabEX will enable a broad range of general astrophysics, from studying the earliest epochs of the history of the universe to understanding the life cycle and deaths of the most massive stars, which ultimately supply the elements that are needed to support life as we know it. These studies will be enabled by the same technology that will allow HabEX to study Earth-like planets, a large, stable telescope in space with unprecedented resolution that is sensitive to ultraviolet, optical, and near-infrared photons. Furthermore, the HabEX concept is particularly compelling, as it is ripe for development, being both technologically and scientifically implementable in the next decade. The HabEX concept was one of 4 mission concepts being studied in preparation for the 2020 Astrophysics Decadal Survey. The study was being undertaken by a Science and Technology Definition Team, STDT, comprised of experts within the community and was being managed by the Jet Propulsion Laboratory. The concept consisted of a 2-part observatory. The Starshade would have been 52 meters in diameter, in the shape of a sunflower, and the cylindrical main spacecraft would have been equipped with a 4-meter diameter mirror, making it the largest monolithic primary mirror launched to space. The Starshade would orbit around 75,000 kilometers ahead of the main spacecraft. The telescope position should have been the one at the second Lagrange point, L2, in the opposite direction of the Sun. However, according to the Decadal Survey, the HabEX Telescope project was not so ambitious. That's why it wasn't chosen. They actually proposed to reinvent its design, for example, substituting the 4-meter primary mirror with a bigger one, with the size of 6 meters. What I really wanted to see was an ambitious, bold vision, like the one the Decadal Survey laid out, said Scott Gotti, a professor of astronomy at Ohio State University and one of the leaders of the HabEX study. If we develop those technologies early, you buy down the risk, and it makes it even plausible that we could have multiple great observatories flying at the same time, which is multiplicatively better than just having one, he said. That's all for this video. Thanks for watching, everyone. What do you think about the HabEX Telescope concept? Let us know in the comment section below. See you next time on the channel.